So it's 10 past.
Okay.
All right. So today we have Jas, who's a postdoc at the University of Strathclyde, part of the UK Quantum Communications Hub. His work in finite resource quantum information helped establish fundamental precision bounds for multi-parameter estimation theory and design practical receivers for quantum detection. More recently, he's worked on satellite-based quantum communications to model QKD rates and has proposed repeater architectures for entangled distributions of vertical spins. So it's my pleasure to introduce Jas and
Thank you. I'll stand over here. Yeah, so thank you very much for arranging the visit. And I understand it was short notice, but being in Waterloo, I thought, why not reach out? So yeah, and also thank you for the introduction. Okay, so as I mentioned, I have worked a bit on estimation theory, detection theory. So it's all a little bit varied, but it does fit under a common umbrella, and that's finite quantum information. So I'll give a bit of a highlight as to what I mean exactly with that. The second part of the talk, I'll then focus on quantum communications with finite block effects. So that naturally arises the need to model these finite key statistics when you're looking at satellite applications, and I'll explain why. And I thought a natural way to go through, some of the features is to introduce the CQIQC software. I'll go through what that stands for, which is our toolkit to model satellite QKD. So I'll go through the modeling framework and go through some applications. And then I'll go through some resource constraints. So as I mentioned, part of the quantum communications hub, we have to now actively work with industry, which was a challenge at the beginning because of, engineering language barrier, but actually ended up being quite nice. But, they basically said, some of the assumptions that we make, they're not actually able to implement. So that was interesting. So we will model that, and I'll come to what those resource constraints are. And then for the final part, I'll go into quantum networking architectures. Basically, how can we use repeater-based architectures with quantum memories to enhance either entanglement distribution or QKD rates, depending on what application you want to look. So I'll pause in between, and feel free to interrupt me at any point if you have any questions. So yeah, I'll try to keep it to around 35 minutes or so we got plenty of time for questions. Okay, so finite quantum information. So really what we mean by that is when you look at some implementation, whatever that is of quantum information theory, it often involves limited resources. Okay, so that deviates from what is often assumed to be asymptotic resources, and naturally then your performance that you kind of establish, it's not so applicable. So the question is, what is the resource in light of finite resources? So when we look at estimation theory and detection theory, really what we mean is, what is the achievable precision? So in estimation theory, you have these well-known bounds, like the quantum Cramér bounds, which basically give you a lower bound on how precisely you can measure parameters. Okay, so that's the study of quantum metrology. But often those bounds are too optimistic, so you can't actually attain them in practice. And experimentalists would then say, okay, what's the point of this exercise if we can't actually saturate these bounds? So, it's coming up with achievable precision bounds. And when we think of detection theory, what we want is to have realizable measurement schemes. So, for example, in unambiguous state discrimination or ambiguous state discrimination, it also comes with bounds on how well you can discriminate states. And then the question is, we ideally want to encode receivers that can be implemented in the lab. That's what I mean. Now, generally, finite quantum information is this transition from asymptotic to finite and one-shot quantum information theory. So it's well studied now, and a lot of people are looking into this. And it involves looking at finite block lengths, entropy inequalities, and these are useful for application in cryptography, computational complexity, and error correction. So generally, what I found, as I've worked through my PhD now and my postdoc, what often this requires is either an alternative construction for your theory where you work from the ground up and encode the limited resource condition. Okay. Or alternatively, if there's an optimization, such as in estimation theory, you add extra constraints that account for limited resources. So this is a bit of an overview in terms of finite quantum information. So this is like estimation theory at the top, distributed and multi-parameter sensing. Here is like the overview of discrimination strategy. So some of this work was actually implemented in the lab. I was as experimental as I got, so I'm quite proud of that. And so in today's talk, I'm going to give an overview of this highlighted blue stuff. So performance limits in discrete variable QKD. So I'll start first with how we model satellite QKD, okay? And then basically extend that to modeling the space-based quantum repeater architectures. Okay, good. So quantum communications with finite block effects. I think this is probably very like introductory level, but I thought for completeness, I'm going to have it. Why satellites? As you well know, really it's to extend the range. The reason is because optical fibers, they have an exponential loss with the range. So you want to overcome the transmission limit imposed by optical fibers, but also it reduces the demand on quantum repeaters. Okay, so and the reason you can do that is it has less noise, so it's not exponential in scaling. And this kind of illustrates. This is a plot from the MISSIUS paper. Okay, the MISSIUS satellite was from China, and they did some groundbreaking milestones to demonstrate that SAT-QKD is feasible. And they have this sort of comparative plot, which the blue line on the top is a satellite to ground link. So they were looking at a downlink in that case. And you can see at 1,200 kilometer distance, the link efficiency, there's a huge difference in loss. Okay. So you can extend quantum networks, and you will do that using a combination of uplink, downlink, and inter-satellite links. There's a little bit of an animation just to show that you can then connect any two nodes through, and then obviously you would want to come up with efficient entanglement routing schemes. But this is basically a precursor for distributed quantum technologies. So the further you can extend the quantum networks, the longer the range of your distributed technology. So that's really what the goal is here. So here it's a bit of a timeline. I wouldn't take too much from it, other than in blue. I know it probably doesn't come across quite well. So blue, I'm illustrating what the demonstrated milestones are. So quite as early as 2010, quantum teleportation with over 16 kilometers was implemented, all the way up to here, which is the MISSIUS satellite demonstrating entanglement distribution and teleportation over 1,200 kilometers. And we're now kind of transitioning to these CubeSat missions. So Spooky 1 is the satellite mission spearheaded by Alex Ling's group in Singapore. And they've also had some demonstration missions. And so there are a lot of proposed missions shown in red. But what I also want to highlight is the number of CubeSat missions. So CubeSat, they're these small units, okay? So they're not like the traditional satellites, and that comes with a limited swap, all right? And already, so that means you can't really have cryogenics, you can't have cooling. So, quantum technology is also already very fragile. Putting it in a space setting, extremely, difficult to then extract keys. I will note that, so for example, 458 CubeSats launched, they're not all QKD. Okay, they are like, for example, Earth sensing, climate sensing. But the point is, they're increasing in popularity. And if we're able to model finite key effects, then so too will we see QKD missions. Okay. So when you're operating in satellite with satellite QKD, there are important operational differences to terrestrial QKD. And the major ones is that now you're operating in a highly variable channel loss. So it's through the atmosphere, you got scattering, you got diffusion, etc. But also you have limited transmission time. So there's only a limited time window where a satellite can talk with an optical ground station. And so what this does is it limits the number of information or bits that you receive, okay, on the ground, if you're looking at a downlink. And so what that means is the statistical fluctuation in estimating parameters are now, they can't be ignored. So you're most definitely not in the asymptotic regime. And so finite key effects are important. Now, as theorists, what we're trying to do is improve the way we handle finite key analyses so that there's a more efficient trade-off in the number of the portion of signals that you receive that are used for key generation for parameter estimation. And if you do that, then ideally, what we will do is reduce the engineering constraints on the performance of sources and detectors, which is a bit of a bottleneck in terms of improving key rates.
You just describe like what you mean by constraints, like what are the parameters you're talking about here?
Yeah. So we'll come on to that on the coming slides. But for example, the sources will have to, have high repetition rate. The detectors will have to have very low, timing jitters. So they need to be performing really well to be able to basically have next to zero loss to get really high key rates. But and so that's very difficult, For example, you can get low timing jitters, but then you need cryogenics, and that's already not compatible with like a small payload. So how can we kind of go around that? That's the type of things. But there will be other engineering constraints, and yeah, I'll highlight what those are. Okay, so yeah, this kind of was the motivation at Strathclyde. So I work with Daniel Loy at Strathclyde, and that was the motivation to develop this toolkit we call CQIQC, which is the Satellite Quantum Modeling and Analysis Toolkit. CQIQC, yeah. All right. So we are working together with a few different missions. As I mentioned, Spooky is one of them. Spooky is the small satellite mission spearheaded by Alex Ling at the Center for Quantum Technologies in Singapore. And they're trying to implement downlink entanglement protocol with this BBM92. I also mentioned the KeySat mission earlier. So that's a local mission spearheaded by Thomas Yenevine at IQC. And they want to implement both BB84 and BBM92 in uplink, which is challenging. If you go uplink, then you have a loss earlier on in your optical channel. So it's a bit more demanding. But they're also doing BB84 in downlink configuration. And this is the UK mission. There's two UK missions, but this is the one that there's more details if you want to have a look at sort of, what the constraints are, what the sort of sizes are. And this is the ROCS mission, Responsive Operations for Key Services. And they want to implement downlink, decoy state, weak coherence ports, BB84. That's how it looks. Hopefully you won't ask me too many questions because I won't be able to address many of them. But this is a 6U platform. So 6U, it's like small satellite missions. They're usually composed of 1U CubeSats, which are usually, kind of toggled together. And this is 6 of them. So that's 1, 2, 3, 6. Okay. And in there, you have to fit in all the optics, the telescope, etc. So it's quite challenging in terms of, basically the point is it's very different to a traditional satellite, which can go up to 450 kilograms, huge. Yeah. Okay, so this is the kind of operation, the specification of the ROCS mission. But what I want to highlight is that in terms of the modeling, we were able to model what the past secure key rate would be. So this was something they wanted to know. And also the question they had at the time was, oh, should we use 100 megahertz for our source rate or 200? I'll go into more details as to what could be considered a more, not optimal, but a better choice. And also asymmetric BB84. Now that's quite well understood in the asymptotic regime, but yeah, we basically said if they could introduce a bias, that would be much preferred. I think if I remember correctly, for now they fixed their optics, so they're not implementing asymmetric, but we did the analysis for that. Okay, so I'm basically going to go through the modeling toolkit because it gives me a good way to introduce how we model satellite QKD. And if there's any questions at any point or something's not clear, just interrupt me. So, okay. So it's available on GitHub and we are iteratively improving it. The link is on the bottom of the slide. We are making it modular so that you can swap and change each of the modules to suit basically whatever loss mechanism that you want to consider. whichever protocol you want to consider, etc. Okay, so this is a bit of the details on the modules. So look, you can see we have a core, orbital, source rate model, channel, receiver, and key. So at the moment, we're only implementing BB84. So the following slides, all the intuition and the graphs will be for BB84. But I am writing like a BBM92 version, and there's also work on single photon source-based protocol. Okay, so I'm going to go through some of those modules. And it'll give, as I said, a nice introduction into how we model satellite QKD. So first, the orbital model. So we need to, for the orbital model, define what our satellite trajectory is. And from there, we want to then calculate what the losses are, because the losses will then feed into what the click statistics will be on the ground. So we introduced this system loss metric, okay? And we define that to be the overall electro-optical efficiency when the satellite is at its highest elevation point. So if we look at a zenith overpass, so the maximum elevation of this trajectory will be 90 degrees. It goes directly overhead. Then at the point t equals 0, which we define to be the highest elevation point, that will be the link efficiency there will be this system loss metric. Now, as the satellite's going around, we impose a minimum elevation constraint of 10 degrees. Missy's took, I think, 5 degrees, but they were able to do that because their optical ground stations were, I think, like in desert, like Delinga, and so there was very little horizon obstruction. But usually, you know, for example, in Singapore, if you had one here, it would be around 10 degrees. That's more like feasible. And then after that, what we do is we construct a single block of all the transmitted signals, and then we impose finite key statistics on there to get, you know, a high degree of composable security. So that's less intensive. Oh, yep. We are doing decoy state, yes. Yes, yeah. And this is basically less intensive than having individual blocks with similar statistics and then accumulating them. But there are different ways there are better ways you can do it. So we do acknowledge that. But so what we do is we take a time window about t equals 0, and I'll go in the following slides how we choose what that time window is, because it's not always best to take the full time window allowed by theta min. Okay.
So you're saying the loss depends on which point?
Yes, yes. Yeah, exactly. So for example, when the satellite is at zenith, it goes through the least amount of atmosphere. But as it goes at a more shallower angle, as you can imagine, it's going through like more of the atmosphere. And so that's the biggest difference. So what we do is we're going to calculate the loss as a function of time. Okay.
What's the usual time scale for this?
For a zenith overpass, it's about 600 seconds. But that's, as I said, that's an ideal one. So it will be a lot less. Yeah. Okay, so the more general overpass is not when it's zenith, but when it's at when it goes to a maximum elevation that's not 90 degrees. So in the code, you can define what that elevation will be. We call that theta max here, okay? And when it's at that highest elevation point corresponding to theta max, then it casts this distance from the optical ground station, which we call the ground track offset. So that's just, we're just giving some names to it, and I'll go into the following slides why it's important. So as the satellite goes along its trajectory, at some point the losses will become too large, after which, you know, the finite key will be 0. That point defines what your key generation footprint is for your optical ground station. So whatever improvements you're trying to do, be it on the engineering side, like designing your sources, designing your detectors, or on the theory side, we are effectively trying to extend the key generation footprint. Because if you do that, the more overpasses that generate more key will give an enhancement. So it'll improve your CQIQC system. Okay, is that... Any questions so far? Right, so We come on to the channel model. So this basically is how we estimate what the loss is per second in the trajectory that you defined. We do two methods. The first method is based on empirical data. And of course, the only empirical data that we have is from the MISSI satellite. So in one of their papers, they did basically say, okay, for this range, well, this is the loss. So from that, we basically extrapolate to all the elevations possible. So you can think of elevation, you know, the satellite trajectory in terms of the elevation, or you alternatively you can think of it as time. And basically they're at zenith, they had a 27 dB loss. Now 27 dB is very optimistic for a satellite QKD mission, especially a small one. So what we can do to model alternative satellite QKD missions is to effectively move this blue curve up and down. So that will account for cases where you have elevation independent losses. Okay, but it gives us a way to model alternative SAT-QKD missions. Now, if you want to fine tune how you estimate your losses, yeah.
Sorry, this was just for down.
Yes, it's for downlink. Actually, we're not. So the difference between uplink and downlink is the shower curtain effect. That when you're doing uplink, the losses due to the atmosphere are at the earlier stage, so you get more broadening, more scattering. We actually are not implementing that effect right now.
Okay.
That's going to be for future. We will improve that. So effectively, what we're doing models uplink and downlink, but precisely it's downlink.
Right. But in the future, the two get these back.
Yes. Yeah. Exactly. Yeah. So this second method gives you a bit better a method that you can kind of fine tune based on whatever you're implementing. So it will depend on your wavelength and your elevation. So the wavelength really comes in into both the diffraction and the atmospheric losses term. So the diffraction, basically, it's the beam broadening. And so what we do is this is standard tools. We didn't introduce this, but how we estimate the diffraction losses is to look at what the power spectrum is across the transmitter. Okay, and then we propagate the beam to the transmitter, calculate what the power spectrum is over the receiver, and then by taking the ratio of them, you can calculate what your losses due to diffraction are. Now, the atmospheric losses, we use ModTran. So ModTran basically gives you a way to calculate what the transmissivity will be through an optical channel, the atmosphere, as a function of your wavelength. And you can basically add like, okay, composition of atmosphere. So it's quite precise, but it's the only non-open access element of the toolkit. But what we've done is we've taken some data sets so you can still use it. But there are alternatives like LowTran, and there's actually a lot more. There's a great wiki page on all the alternatives kind of software to estimate what atmospheric losses are. So that's something also that we can think of improving. So everything is fully open access. And then we have this eta int, which is basically your internal losses, and it's constant. Okay, so it wouldn't depend on elevation. And so this gives us a way also to construct that elevation dependent loss curve. Okay, and then the error modeling, we basically pull together errors associated with your sources and your detectors, and it just gives us a nice kind of way to look at what the sensitivity of your finite key will be in terms of error associated with your sources and detectors. That's all it is. And we'll come on to that kind of trade-off later when we look at some applications. Okay, so this is the finite secret key length that you can get with the 2 decoy state BB84 protocol. So this was the key rate that was looked at by Charles Lim. Okay, and because we're using weak coherent pulses, there's a non-zero probability that you'll get multi-photon events. Okay, so that's susceptible to photon number splitting attacks. And so this blue term here is estimating the number of bits that you can get from single photon transmission. The red one is the number of bits that you can get from vacuum, but most of those will be uncorrelated. They can get dark counts, etc. And so that's where the error correction term comes in, which is basically the number of bits you have to subtract to account for that. Okay. And so the finite secret key length is determined from your finite data blocks. So we're basically estimating the number of clicks that we get at our optical ground station, and then we impose our finite key corrections. That correction is this delta term. Okay, so these are modeled using tail bounds for probability distribution, and we use the multiplicative Chernoff bound. We played around with quite a few different tail bounds, and we just found that this worked quite well. It always gave like a higher secret key length. Okay, so we're coming towards like the end of all the modules. What we do is we optimize the secret key length over the protocol parameter space. Okay, so that's the intensity values, the probabilities that you transmit those intensities, and the basis bias, which I haven't written here. But there is an additional important optimization parameter, and that's the transmission time window.
Sorry,
Yeah.
Do the correction terms depend on your block size?
Yes, they do. I haven't shown that, but it's quite involved actually. But they do. Yeah, actually, so too will the error correction term.
Okay, so that was something you guys looked at, like.
Yes.
how-
Yeah. So when we talk about optimizing all this, actually the equation is a bit involved.
And does it depend on your variance of your transmittings?
Yes.
Or-
Yeah. Okay. Right. So the additional optimization parameter is that time window. And the reason is we are, as I've said, we're operating in atmosphere, so it's a highly variable channel loss. So the expected observed statistics vary compared with when the satellite is at zenith to when it's at a low elevation. And data at low elevation has both small count rates and high quantum bit error rates. And so what that means is we can actually optimize further the secret key length by truncating poorer quality data. And that's just an important trade-off. And so if we have a look at our overpass, we impose this theta min elevation constraint. So we don't consider any data. And we effectively chuck away everything in that red shaded region. And we define the blue segment as 2 delta t. So delta t about time t equals 0. And we want to optimize the secret key length as a function of delta t. Okay, and what we see is that for 27 dB, so that's the black curve at the top, that's what Mrs. was considering. We see that if we look at the secret key length as a function of delta t, the time window, it's always increasing and it just plateaus off. Okay, so basically it's saying consider the biggest block size that you possibly can. But the situation changes when you're looking at larger losses such as 40 dB, which is typical for your smaller satellites. You actually start getting this drop off. Okay, so actually the secret key length per pass becomes smaller if you take the time window to be too large. And that's exactly what this is basically highlighting. And the reason of that is you get a better average quantum bit error rate for the overpass. So that, I mean, when I first came across that, I was a little surprised because we're already working in a finite block size. I thought, you want to get everything that you can, but actually what really becomes important is how the average channel, it's very sensitive to finite keys. And so actually truncating it even further is better. And I do want to mention that actually, there are ways where you can actually segment the overpass. I have no neat way of showing this, but we can consider not just this one, we can consider multiple segments. We haven't done that, but it will give you not an order improvement, but a bit of an improvement in your finite keys. Okay. Right. So that's basically the optimization module. That's all it's doing. So it's just a numerical toolkit. We apply that in Python, and we've got a documentation that does need improving. It can do with a lot more examples of use, demonstrating a lot of how the modules are working. But we're updating that iteratively. And yeah, if there are any protocols at this stage, before I forget, that you want to contribute to, then just reach out. It's something we're always looking for. And as we look towards the applications that I'll show you in the following slides really were born out some of the analysis that came through interactions with the engineering company that we were working with, Craft Prospect. So that's just one of the local engineering companies that's working with the communications hub that are trying to develop like a small satellite mission, the ROX mission. And yeah, there's key generation analysis and basically look at different applications. So I'm going to go through those in the coming slides now. But any questions on in terms of the modeling? Yeah.
I'm
So far?
assuming that when you model the loss, there's like the loss changes due to certain like short-term effects, right? Just because of like environmental disturbances.
Oh yes, yes, yeah.
Do you know like what that density of the loss function is?
So we don't do that, but we basically try to find what per second the loss is.
Mm.
There are folks who are like actually looking at beam propagation through the atmosphere, so it's more like a stochastic process. We don't do that. We're using basically we offload all that to Modtran, which is basically saying, okay, at this elevation and this wavelength, this is the loss. So it gives sort of an order approximation, which yeah, like taking that approach, I think it's good, but there's also a caveat because we don't really know if that really follows empirical data. So that's just my thought, though. That's not, I wouldn't say that's widely accepted, but that's just my thought. Yeah.
Is this issue of having a variable transmittance only a problem when you have finite keys? Like if you were to go in the asymptotic regime, would it still be an issue?
You definitely see that as an issue for finite keys because it becomes more susceptible to any sort of variation. In the asymptotic regime, not so much. Yeah. Does that answer your question? Any other questions? Yeah.
Modeling question, you know the channel property, you know the loss. Is that the valid model because of that you measure that you have something for web, so when you have to
Yes. Okay. That's something I didn't mention. Yeah. So we are assuming clear night sky operation, very good weather. That stuff really does get, so we do have a term actually in the code, which is like your dark count, background dark count. And you can set it to value. So we set it at a value which is elevation independent, because there's very little literature that I found at least that looks at the elevation dependency. That we thought of doing an experiment. I'm serious, so that comes with a bit of side caution. But to look at this elevation dependency. But what we found when we stick it to specific values, we set it to a value that corresponds to, as I said, clear nighttime operation. If you set it to like a value that corresponds to daylight, you almost get 0 keys.
How often does it happen? Clear nighttime operation, and you say that 10% probability or 1% probability, but how often is it?
Oh, so it depends on your overpass. Like if you have like a sun synchronous orbit, you will get quite a few overpasses which you can use that match those conditions. But then it's the weather. That's the caveat. The weather still needs to be very good. Yeah. So that I think will be a major bottleneck for satellite QKD. So there's a lot of work to be done. Like a lot of the key rates that will demonstrate, they're not that high. So we're already at this kind of interface between 0 key, so any fine tuning we can do, this is really what we're trying to do at the moment, trying to improve the robustness. So we got a bit of window if there's, poor weather, so we still get keys. Yeah.
Oh, you said that, the reason why it doesn't perform as well in the daytime is because of dark times, right?
Yeah, basically you're getting a lot of background light signals, clicks, and it's adding to the quantum bit array. And if it goes too large in the finite key regime, it's basically going to say 0 key because you have that limit.
Is it possible to transmit at like a certain very specific wavelength?
Yeah, so there are different optimal wavelength choices, and that becomes even more important for daylight operation. We don't do that here, but I know some folks have worked on it, even at like Strathclyde. That basically minimize that loss. Yeah. If you have a look at like the loss as a function of wavelength, there are these sort of kind of peaks where you can choose your operation to be. Yeah. Okay. Yeah. So I'll quickly go through some applications and then I'll go into the networking side. So as you remember, we had these two loss categories. You know, those are broad brushstrokes and saying, okay, all the losses, we're going to pool it together based on whether they are source-based or detector-based. So you get these characteristic lines that this is not really surprising. If you're increasing your probability of your extraneous counts, then you're going to get a net reduction in your secret key length. And we see the same thing for your intrinsic QBA. So this slide is not really surprising. So I'm going to gloss over it. But what might be insightful is the trade-off. So here we're plotting the secret key length, which is going vertically. On the x-axis, if you like, is the probability of extraneous counts. So that's the quality of your detectors, if that's how you want to think of it. And on the y, you have your intrinsic quantum bit array, errors associated with your sources. And what this is illustrating is, irrespective of the value of, there are certain values of PEC that you'll always get zero key, no matter how much you improve your performance of your source. So for near-term improvement, because ideally you want improvements in both, for near-term improvement, it pays to improve background light suppression and detector top counts. So improve your detectors, basically, is what that statement is saying. Yep. Again, that wasn't too surprising, but at the time when I was looking at it, I thought it was, oh, okay, that's neat. But that's because I had no experimental background or intuition, probably. But yeah, I thought that was nice. Another thing we can estimate is your annual secret key length. Okay, and the reason, so here we are plotting the secret key length as a function of that ground track offset. So basically, we look at an overpass with a particular elevation, say 90-degree elevation, so that's your zenith. And for 27 dB, which is the black curve, that will give you a dot. We repeat the calculation with a maximum elevation of, let's say, 66.4, whatever, that will give you a dot. And we were doing that all the way until we look at an elevation which gives 0 key. And this shaded region is your 10-degree limit. So we're not constructing any keys in that region. And then from the area under each of the curves, we can estimate what your annual secret key length will be. And that's the equation we use. And the reason is what we estimate a sun-synchronous orbit as a polar orbit. So that's how the satellite trajectory looks. Oh, sorry. Yeah, very hard to control the point of that. Anyway, so the shaded purple, it looks more clear purple on the computer, but yeah, the width of that is your key generation footprint. Okay. So as the Earth is rotating under the satellite's orbit, the optical ground station, wherever it is, let's say it's on the equator, will intersect the key generation footprint. The more times it intersects it, the more key you will get. So at a higher latitude up here, that will happen more often, right? And so because of that, you'll get more overpass, and it intersects it uniformly. That's the key assumption that enables us to estimate from this formula. And the more intercepts, the more key you'll get, and that's basically what this annual key equation is saying. Okay, so for the losses on the legend here, we quantify what that is. So, yep. Yes. So, when you say other orbits, like elevations.
Yeah, or like, the satellite going equator or that angle, or not necessarily circular, but more elliptical orbit.
Okay. So we do look at like sun-synchronous orbits. We haven't looked, but if you're on a sun-synchronous orbit, then by orbital kind of geometry, you can make them equivalent to looking at a particular elevation. So that would be modeled, but we haven't looked at, like, for example, geo. But the same should hold.
Okay, and this is a low Earth orbit?
This is a low Earth orbit, yeah. We're basically trying to model the Messias satellite. That was kind of the motivation at the beginning. Let's see how close we can get to it, and then we're trying to now extend our analysis to the small satellite missions. So yeah, low Earth orbit.
why do people choose this polar orbit?
Oh, that is just to enable an estimate. And it's a good approximation. But we only do that for the estimate of your annual secret key length.
But that's the worst case scenario, right? If it's going in the same vein as the Earth orbit, then there will be much more afterwards.
How do you mean? So we are looking at different.
So right now the Earth is rotating this way and the satellite is rotating this way. So there are 2 points basically that they can just
So okay. That assumption is only for this key length, but it uses the integrated secret key length, which accounts for the different overpass trajectories. Yeah, that's basically this, the secret key length integrated. It's not very clear. And that's the area under each of these curves. Okay. Yeah. So we estimate how much it would be. So for 27 dB, we get like 0.91 gigabit bits as an estimate. And for 40 dB, and I always stress that's more what we're operating at for these small satellites, we get 2.8 megabits. So it's very small. Now, there are some approaches. So this is assuming single overpasses, data constructed from single overpasses. So we can look at agglomerating data from multiple overpasses, and that's what this thing is doing here. I haven't defined what system A, B, and C is. It's basically different operating source errors, detector errors. It's the cube intrinsic quantum error rates and the extraneous count probabilities. At this point, I don't even remember what those values are, but it's on the paper here, in this one here. Okay, so yeah, you do see an increase, but then I personally think it's worth, I think it's a security vulnerability. Like if you have an overpass, you need to store that data, you need to secure it, you need to wait for a suitable overpass, a second overpass, store it, and you keep doing that. I think that's a potential security vulnerability. So ideally, a lot of the analysis that we try to illustrate is with single passes. If you can improve that, yeah, I think that would be really the ideal go-to. Okay, and so the protocol performance, I briefly mentioned when I was highlighting the ROCS mission, one of the specifications was looking at asymmetric and symmetric BB84. We did an analysis for that. The asymmetric is this, it's not very clear on the screen, but it's the solid curve, and the dashed is the symmetric. So there is a lot of performance improvements owing to higher secret key length and also more overpasses that generate non-zero keys. And the other, yep.
So the multiple passes, the lab infinite passes, also
We show it tends to the asymptotic.
how much higher would it be?
So in this case, you already sort of see a plateau. Yeah, we look at that in the appendix for this paper, but you're not too far. But I mean, so this is the key length normalized by the number of passes. So it's not illustrative of what the secret key length is, but you can calculate it just by multiplying it by this. But here we kind of show that for 8 passes, you're already kind of tending to what the asymptotic would be. And really the reason is you get bigger block size, then immediately the way the processing becomes more efficient, the overheads become more efficient. And
so once you go to multiple passes, I understand what you're saying. So do you use the same decoy state intensity for all the time?
yes, we do.
Okay,
So this analysis,
multiple passes can go and do that, like you can change the
yes.
Yeah.
Yeah. So when we did the number of overpasses, we assumed everything was fixed. So again, that is a bit of a caveat. Yeah. So I think we would see a bit of an improvement. It wouldn't be like, again, an order. So all of these are really estimates. The way we model the losses, there's not too much finesse to it, I would argue. But we would see a bit of an improvement if we were to change it on a per pass basis. Yeah, I agree. And so on this graph, sort of touching on what you just asked, so Missy's originally implemented 100 megahertz and are thinking of doing 200 megahertz. Some of the missions they're mentioning, I don't know if they're actually implementing, I don't know. From what I could tell, I don't think so. They're looking at these ultra bright sources going really to 500 megahertz, gigahertz, even for like NEO, and that's like the NASA Deep Link. That's sort of what they were proposing to do. And yeah. So what we did was we looked at what the secret key length as a function of your source repetition rate is. And if it's too small, basically you're not getting any, your block size is too small. So this is like the key suppressing regime. You're not going to get any key, 0. After like some critical value, you'll get a superlinear scaling. And this is just illustrating the finite block dependency, okay? And we basically looked at what's the natural choice for your source rate that could give robustness to different losses. That's what each of these sort of losses curves are showing. And we said about 500 megahertz. So we kind of stuck with that for the analysis. I think you don't want it too large, because as I said, if it goes too large, you need better performing detectors with low timing jitters. You need cryogenics, like superconducting nanowires can do that. Ideally you don't want cryogenics though, so there's a trade-off. Okay, so I guess next part is the resource constraints. Any questions so far?
So, yeah, just to clarify, the reason why this supervision rate plateaus with respect to the source repetition rate is because of like the dead time.
No, so you mean this part, where we're looking at the multiple satellite overpasses? Oh, here. Oh, right. No, so here it's basically as you increase your source repetition rate for a particular orbit, everything is fixed. All you're changing is the source repetition rate. Your data that you're collecting at the optical ground station is becoming bigger. If you like, it's tending towards an asymptotic block size. So basically the finite key effects are diminishing. It's you can more efficiently do the trade-off between key generation, parameter estimation, and that's why you're seeing this tail off. Basically, if you were to draw a straight line for the asymptotic for this system, it would be somewhere like here. Okay, so the different curves correspond to the different PEC Cuberi values.
It's just the per pulse, right? It would increase the effect if you increase repetition.
Yes, yeah, it would. But I guess my point was, you want to increase it, but you don't want to increase it too much so that you then have to rely on cryogenics, better detectors, which are a bit out of reach. So what would be a natural choice that gives robustness to a variety of different losses? No, that's what we're trying to illustrate. Because I think the intuition is already there, but what can we illustrate in terms of numerics? Is that? Say again, sorry?
So do you consider that detector gap?
Yes, yeah, we do. Yeah, we do. That's a good question. I don't remember what we set it to, but again, it's a constant value. We don't change that. I can find that after the talk. I think you had a question or no? Okay, good. Right. So next part. So this was, I think, one of the questions, Reem, that you had, which was what are the resource constraints? So far, even though we're looking away from the asymptotic regime, we're in the finite key regime, it's still of sorts an upper bound to the expected performance. And the reason is, as our engineering friends told us, it's hard to engineer dynamic control of all the parameters, and we're optimizing over those parameters. So that means they're free to change on a per pass basis. And so they said, okay, some of these parameters, you need to consider them fixed because we just can't change them. In addition, there's size, weight, and power constraints. And that limits, for example, the amount of storage you can have on board. I'll describe what I mean by that. And all of these really compound the amount of keys you can get. So we want to illustrate how much of an impact does it have and what could be the natural choice. Yep.
Well, what are the parameters that you want to fix because you want to control?
Coming on to the next slide. It will, yeah. So fixed parameters. Those are the receiver basis bias and your operational pulse intensities. Now, that's what our, as I said, engineering friend says. Basically, the receiver basis is on the optical ground station. You have to fix it with a kind of passive beam splitter. It's hard to like take it out, put it back in. That's the reasoning that was given to me, and I was satisfied with that. So it's hard to change that on a per pass basis. So you have to assume that's fixed. And your pulse intensities on board your satellite, basically the way they construct the laser drivers is basically they want to have it fixed. They don't want it to variably change, although it's possible. It just opens up the possibility of something breaking. So it's really to improve the robustness and drive down costs. They consider it fixed.
You can just start with your A, like a pencil. Or
You can change it, yes, but we wanted to look at, okay, say if it is fixed, what could we do? And they don't do any sort of control to mitigate it.
So the satellite has the receiver, right?
No, so we're considering a downlink. The receiver is on the ground station. So in principle, you could change it, but it would just still be difficult. So the mission, they basically said they wanted to consider it fixed, but the source will be on the satellite. So what we did was we did an analysis where we assumed we're going to take these parameters to be fixed. And we wanted to say, if they're fixed, what's the optimal fixed values? If you want to talk about optimal, then you need to choose what your figure of merit is. And we chose it to be the annual secret key length. So what we did was we basically assumed you can change them. So we're fully optimizing it, and that gives you a black curve. That's the secret key length as a function of ground track distance. We've seen that on the previous slides when we were looking at the integrated areas. And then for each point along the curve, we extract the values, the optimal values for the receiver base bias and your pulse intensities. And then what we do is, for example, this point, we take those fixed values and we rerun the curve, okay, optimizing the remaining parameter space. So you can see the blue curve, it kind of hugs the black curve, but then there's a slight deviation here. It's expected, I guess, right? And then you do the same one with the other extremal point, you get a deviation on this side. So it's like, okay, so if we have that, we can calculate the secret key length, the annual secret key length. That's what we do here. And from that, we find the fixed parameter set that maximizes the annual secret key length. And that gave us these values. And that was sort of like a fixed bias, a receiver basis bias of 0.8 was in order of what the experimentalists were already sort of looking at. So it was kind of close to at least, what they were already applying. So it was quite neat. And this approach can be generalized to any fixed parameter set. And in terms of the receiver basis bias, I wanted to illustrate some sort of intuition as to what's happening. If you fix it to some values, you're effectively fixing the portion of your received signals that you use for key generation. Okay, so the larger it is, so if we have a look at this plot, the larger PXB is, the secret key length will increase because you're using more of that portion for key generation. But if you set it to be too large, you leave too little for parameter estimation. And so actually you do, so for example, a large value, you do get like a kind of tail off here. What that means is there are some overpasses that will generate non-zero key. So there again is a trade-off, and that's sort of what we were looking at. The black curve is the optimal, where we don't set it to any fixed value. Right, yeah. Now, on the right-hand side, we were trying to see what the intuition on the transmitter basis bias is. Generally, if you're fixing the receiver basis bias, the transmitter bias will vary to compensate. Okay, but if you optimize both, then having them equal is the optimal choice, and that's the black curve in this case. Okay, so as a final constraint, it's limited onboard storage. So what do I mean by that? Now, for prepare and measure protocols, you need quantum random number generators. but they are a bit demanding in terms of onboard processing. And so one way around that is to generate random bits at a lower rate, okay, using less powerful random number generators and storing them. But that assumes that the transmission duty cycle is less than the orbital time. So what I mean with that is basically the satellite's trajectory is out of the field of view for your optical ground station. It's slowly accumulating and storing the bits. And then when it comes to transmission, it's very quickly transmitting it. But the thing is, if there's an onboard storage limit, then there's only so much you can store of those random bits. And we're going to model that impact. So each pulse requires 7 unbiased bits from the quantum random number generator. And if we're considering 500 megahertz, then that means you need 2 gigabits per second. Current space validated random number generators operate at around 1 to 20 megabits per second. So quite a big difference, unfortunately. And so this is what we're illustrating here. What the secret key length is as a function of your ground track distance for different memory buffers. So how much like bits you can store. Obviously, there's going to be a big impact because if it's too small, you can't even operate your source for the whole time window. And the red curve here illustrates what the minimum buffer required is for non-zero key. Okay, and this is just illustrating what the annual secret key length is as a function of your memory buffer. So it's basically saying we want, ideally higher the better, but at 128, you're already saturating the asymptotic case. All right, any questions? And then there will be a few slides on quantum networking.
What is onboard storage, value of cost and size of satellite?
What's the cost and size of your onboard storage?
I mean, we want to limit this to increase the cost of satellite. Is it the way we...
So I would say that we're trying to not rely on intensive quantum random number generators. So using onboard storage is a way around that.
The reason we don't want to rely on them again is to decrease the size.
Yeah. Oh, yes. Yeah. Yeah. Sorry. Yes. Yeah. 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 Okay. Right. So quantum networking. So I have like another, I think, 5 slides, and then I'll be done, and then we can take any questions. So, a bit like Stephanie Werner, she had this roadmap for quantum internet. I wanted to not necessarily generalize it, but add the sort of space segment element to it, which I thought was missing. So that's what this roadmap is illustrating. Each of these will be networks with increasing maturity. So take it with a pinch of salt. This is sort of what, you know, we illustrated in one of the review papers that we wrote. But basically, we do want to use memories. And then, you know, you will go from less mature networks, such as trusted repeater networks, to entanglement distribution and routing networks, to, if you use memories, you can then implement operations that require high latency. You can do entanglement swapping deterministically, okay? And that will enable a lot of applications such as blind quantum computing, clock synchronization. That would be useful for imaging sensing protocols that I used to look at and assume in my PhD days, but yeah. And then, you know, these are really look into the future, but where you start implementing fault-tolerant networks and then quantum computing networks. But the point is that we want to analyze what the performance could be if we start looking at memory-assisted quantum networks. This figure was from one of the review papers, so if you want to see more details of that and explanation, I would refer you to that. It's called Advances in Space-Based Quantum Communications. I'm very bad with titles, even of my own papers. Okay, so what's the bottleneck? So for long-range communications, we've already gone through this really, but this is just to, again, summarize. You can use quantum repeaters, okay? So you establish independent entanglement links between neighboring nodes, and then using like Bell state measurements, you can swap entanglement and teleport entanglement, and until you get entanglement between 2 end nodes. You can also use satellite-based QKD, which we've already seen and has been demonstrated. But unless you consider like a trusted satellite repeater, both will be limited to a few thousand kilometers. Okay, so what if we combine both approaches? So if we use memories on board satellites, so that's going to be really the theme of the coming slides. So memories improve the rate loss scaling by synchronizing probabilistic detection events. Okay, and so we've looked at that in terms of what kind of architecture can we have with memories on satellites to establish, in this case, we were looking at entanglement distribution rates, so we didn't want to confine it just to QKD. And here work with the Berlin group of Jens Eisert at Free University. We looked at like modeling event by event simulation, seeing what sort of fixed repeater architectures could improve key rates. And then more recently, we looked at a single satellite case. So I'm going to summarize these in 2 slides now. So using satellites with quantum memories has been looked at previously, not by us. So this was a paper by Boone, and Thomas Yenevine was involved with that. So that's like, again, a local person. So the idea is if you want to connect or distribute entanglement between 2 nodes here and all the way here, then you can use satellites to distribute entanglement photon pairs. And this intermediate ground station will have a stored quantum memory. And this quantum non-demolition measurement basically detects the presence of a photon. So it's heralding, basically. Okay, so it's a deterministic process. And then it'll do a Bell state measurement, and then you have entanglement between these 2 ends. So what we thought, well, in atomic physics, they already, and I was very surprised about this, they're already putting quantum memories in space. They're looking at fundamental tests of physics. So, you know, if you can accept that, that's a reality, then we thought, all right, what if we shift this part, this segment onto another satellite? That's minimal change, but that's what we did. We put all of that onto a satellite. So this satellite now has a quantum memory. And immediately, it has several advantages. So you should expect a performance improvement, and we'll just quantify that in the next slide. So now only 2 atmospheric links go through the atmosphere. So you have a lot less noise and loss, and weather effects now only depend on these 2 links. So previously, obviously, if these 2 nodes were far, you will need a lot more satellites, more links through the atmosphere. So that's good. And also the Doppler shift compensation is reduced because the relative velocity of each of the nodes is smaller. So we just quantified that. So this is the DLCZ scheme using quantum memories with atomic-based platforms. Okay, so they're performing, this is the entanglement distribution as a function of the total link length. So that's their performance. But the limiting factor for this is the classical communication rounds. You have a factor of L over C, effectively. Okay, that's the range, L, and the time taken is L over C, to herald entanglement distribution, like a Bell state measurement. So that's the limiting factor. Then the Boone protocol, where they had the hybrid, like the memories on the ground, but using satellites, it performs immediately better because you can have greater range. But the scaling doesn't go quite well with the link length because the further the range is, it goes through how to describe it, the link becomes quite shallow. It goes through a lot of the atmosphere, so that it basically kills off the rate.
So for battery time reduction.
That's a good question. In the order of a few seconds. Yeah.
How long does it get for a satellite to go around?
A lot more than that. Like for a satellite to go around the Earth, would probably be or in the order of minutes. I don't know precisely.
So in the long term future, I suppose a battery can long, so the satellite go around,
Yes,
then you don't have to think about.
we're going after that.
It's one satellite, the satellite.
Yes. Yes, yeah. It is the limiting factor, but there are works looking at ultra long-lived quantum memories, We're going to come on to that in like the next slide though. So the final one was the space-based protocol, where we have like memories on a satellite. You get an improvement like overall link lengths. But there is a caveat, which is we need a lot more satellites constellation. I think that's challenging. So that's not really immediate term. If we think of feasible, which I always have been, it's not very feasible. So we thought, right, there you go. Minimize the storage time required. So roughly 70 milliseconds. So not even seconds, but at 10 to the 4 kilometers. Right, so yeah, you can use this entanglement distribution time to estimate what your storage requirement is. So we came up with a second proposal, which now only uses one satellite, and it uses an ultra long-lived quantum memory in the order of 1 hour. So that's apparently what the experimentalists at Berlin were doing. So we were like, okay, what can we do with it? So the idea here was the previous proposal, the constellations grew too rapidly. So it's difficult to implement, resource intensive, etc. So the idea, what if we use a single satellite with an ultra long-lived lifetime to physically carry the quantum information? And I'll illustrate what I mean with this. It's better through a picture. So you have this, one of the nodes like we did on the previous pictures. And the satellite now has two memories, quantum memory 1 and 2. Quantum memory 1 is an ultra long-lived quantum memory with a lifetime of around 1 hour, in the order of an hour, let's say. And this one is in the order of milliseconds, but we'll go into that. So what's happening is the entanglement photon pair is sending one to quantum memory 1, and the other is being transmitted to the first node. So if there's no click detected, i.e. it's going through the atmosphere, it's lost, then it's basically saying, okay, flush out that memory in quantum memory 1. We don't want it. If the photon is received, then you send a classical communication and you say, okay, store it. So now you've got like a herald, you can do a heralded, basically. That's the idea. And then as it goes over the second optical ground station, it's doing the same thing, but now it's doing it with the shorter lived quantum memory. Same thing, same thing, same thing. Okay. And as soon as you have photons stored in both, you can do a Bell state measurement. Now, the use of ultra long-lived, so these are the relative timings. Okay. The use of ultra long-lived quantum memories has previously been looked at, not by us, but that scheme didn't look at the second quantum memory. And I'm going to show that does have quite a big impact. So this is the comparison between those two schemes. So the single memory case, the solid curve shows you what the finite key length is, and the dashed is the asymptotic. The reason there's a big difference between the two is just because without that second quantum memory, you're not getting many pairs that are transmitted. And so it imposes basically a huge finite key penalty. Now, when you consider the double memory case, the finite key that you can get, the key rate, improves, and it's also much closer to the asymptotic, its corresponding asymptotic rate. However, the asymptotic case for the single memory can still outperform the corresponding asymptotic key for the two memory case. And the reason is because when you have the two memories, you now need to account for non-ideal Bell state measurements and additional dephasing noise for the second memory. But really, practically, you're only going to be considering these solid lines. So we get a bit of an improvement. And we also looked at like the key length that you can get. So having two memories, you can get up to a factor of 10 to 3 advantage, which is quite dramatic. Okay, so just future directions, sort of to wrap up. You know, if you're going along this theme of quantum networking, what is interesting is to look at different topologies to enhance the performance. So it depends, are you looking at QKD? You're looking at entanglement distribution rates. Then you want to look at link scheduling, which will become more important as well, and explore distributed applications. So one thing I think would be nice is to look at distributed quantum computing, where you implement non-local quantum gates. Sort of trying to look into that, but that's really early days. And some challenges, well, there's quite a few. I think that the list doesn't do it justice, so I'll leave that there. So in summary, finite key effects are native to satellite UKD. It's important. We have a numerical toolkit, and we're basically now starting to look at how we can implement networks. And yeah, there's quite a lot of future work, and I want to thank like the co-authors that were part of all this analysis work today. And that's it.